So today we are going to be looking at frequently used negative feedback op-amp circuits. And I'm being honest, this should mostly be a review. Some of you may not be familiar with integrators and differentiators, but for those of you that advocate for circuits two, you've seen, or excuse me, circuits one, you've seen them before. All right, so the first one that we're going to look at is the most commonly used circuit, and that is the inverting amplifier. And it is actually the circuit that we dealt with in class last Friday. So in an inverting amplifier, we have something like this. Here's our our inverting input terminal, our non-inverting input terminal, positive supply voltage, negative supply voltage. Here's our output voltage. All of these are going to be negative feedback circuits. So I'm going to place a resistor in the feedback path, connecting my inverting input to my output like so. I'm going to call this resistor R2. There's going to be a resistor R1 between my inverting input terminal and my input voltage signal Vin. And then we are simply going to connect our non-inverting input terminal to ground. So our ultimate goal for all of these circuits is to derive a relationship that tells us what V out is as a function of V in, or at least for these first few where we only have a single input signal. We'll do something similar for later circuits where we have multiple input signals, okay? We're going to derive these relationships by just applying those ideal op-amp rules that we talked about in our last class meeting, because since every one of these circuits is a negative feedback circuit, we know that we can treat them as if they were ideal op-amp circuits without losing too much information or introducing too much error. So with that being said, our first ideal op-amp rule tells us that there can be no current flowing into or out of our input terminals. So we know that both of these currents are 0 amps. The voltage present at the non-inverting input terminal we can see is 0 volts by inspection, which means the voltage present at the inverting input terminal must also be 0 volts because of ideal op-amp rule number 2. Writing a Kirchhoff's current law equation at our inverting input node means that we're just going to add these two currents that I have denoted in green. And so that's going to look like 0 minus Vn, or negative Vn divided by R1, plus 0 minus V out, or negative V out divided by R2, is equal to 0. And this can be easily rearranged to find that our output voltage V out is simply negative R2 divided by R1 times Vn. So that's our relationship. As output voltage as a function of input voltage. From this, we can very easily find our closed loop voltage gain. So our closed loop voltage gain, AVCL, is just the ratio of V out to V in. And that's going to be simply negative R2 over R1. All right, so let's talk very briefly about why this is the most commonly used topology. Okay. To put it simply, it's the most versatile. So what I mean by that explicitly is depending on what values R2 and R1 have, we can either introduce some amount of amplification, meaning that our output signal is larger in magnitude than our input signal, but we can also introduce attenuation, meaning that our output signal would be smaller in magnitude than our input signal. Okay. So we can do either with this particular type of amplifier, both amplification and attenuation. However, um, because we have an inverting amplifier, the output signal is going to be of the opposite polarity of the input signal. And we see that very explicitly by seeing that there's a negative sign in the voltage gain. So we can create a different amplifier simply by swapping where we apply our input voltage and ground on the input side of our circuit, and that will give us a non-inverting amplifier. Something like this. Once again, I'm going to put my inverting input terminal on top. Here's R2 yet again. This circuit is going to look practically identical to our previous one until I get around to applying VN and ground. So here in our inverting amplifier, we applied our input signal at the left-hand terminal of resistor R1. Now we're going to apply ground there. And in our inverting amplifier, we connected our non-inverting input terminal directly to ground. Now we're going to apply VN there. So it's literally the exact same circuit, except we're just swapping those two voltages. But we're going to see that we get a pretty darn different input-output relationship. So using the exact same procedure as before, we know that there are no current flowing into or out of the input terminals. By inspection, the voltage present at the non-inverting input terminal is simply Vin. Applying ideal op-amp rule number 2, that means the voltage present at the inverting input terminal is also Vn. Now we write our Kirchhoff's current law equation, adding these two currents together, and what we wind up finding is that Vn divided by R1 is the current flowing to the left, and Vn minus V out divided by R2 is the current flowing up and to the right. And this can be rearranged such that V out will be equal to 1 plus R2 over R1 times Vn, and therefore our closed loop voltage gain is simply 1 plus R2 over R1. So In a non-inverting amplifier, we can see from our closed loop voltage gain that this type of circuit is only capable of providing amplification, meaning that our voltage gain will always be 1 or greater, right? If R1 is significantly larger in magnitude than R2, then our voltage gain is going to look like a number very close to 1, but it can never be negative, and it can never be less than 1, okay? So it actually has more limited applications because of this constraint. Now, one thing that I want to point out, and I'm going to kind of try to zoom in here so that we can see both of these at the same time, is the differences, right? Or actually, not necessarily differences, because I feel like I've explained that, but how we can easily identify what type of amplifier that we have. Because these two are so incredibly similar, sometimes it's difficult to sort things out. And the shortest answer is we just need to look at which of the input terminals that our input signal is applied to, right? So in the first circuit, or the circuit on top, our input signal is applied through some resistor network, but it's on the inverting input side of the amplifier. In the second circuit, our input signal is applied on the non-inverting side of the amplifier. There's nothing stopping us from putting a resistor network on the non-inverting input side of the amplifier as well, but that's generally speaking how we're going to tell the difference. If the input is on the inverting side, it's an inverting amplifier. If the input is on the non-inverting side, it's a non-inverting amplifier. Zoom out. Oops, zoom in, I mean. Okay, so let's talk about a special case of this guy really quickly. So let's say that when R2 is equal to 0 and R1 is equal to infinity. So effectively, if we replaced the resistor R2 with a short circuit and we replace the resistor R1 with an open circuit, what would our closed loop voltage gain look like? I disagree. It will not be 0. Mm-hmm. Yeah, exactly 1. So our closed loop voltage gain will be exactly equal to 1. This configuration is what's known as a unity gain buffer. It is literally just a special case of a non-inverting amplifier. So a unity gain buffer is something that you're going to see used in a lot of instrumentation and control systems. Effectively, whenever you have a sensor that is providing your input signal or your control signal, you usually use a unity gain buffer such that effectively the power that's sent along is provided by the supply rails of the op-amp circuit and don't have to be generated by the sensor itself. Okay, so you might have a sensor that measures some amount of mechanical deformation. Okay, so there's a special type of materials called piezoelectric crystals that generate electricity or a voltage in response to mechanical deformation, right? So you can make all kinds of neat strain gauges and all of that kind of stuff out of them. Well, they're really, really good at making voltages, and they're absolutely terrible at producing a current. So we use a unity gain buffer to effectively have a separate stage that allows later stages to pull current from the supply rails of the unity gain buffer, not the sensor itself. So that's what these are used for, and you're going to see them a lot as you go out into industry, particularly if you go into like chemical processing plants and all of that kind of stuff where you're developing large scale control systems. So just wanted to make a note of them. All right, the next circuit that I want to look at is what's called the weighted inverting summer. So let me give myself enough room here to have multiple inputs. So here's our basic op amp. This plus, so I'm going to start, as I have with all of these, with my feedback resistor. We're not going to call this R2 this time, and we'll see why in a moment. I'm just going to generically call this resistor R, or you might see it in some literature as RF for literally feedback resistor. On the non-inverting input side, I'm going to have multiple resistors. So we could do this one as R1. We could put another one up here as R2. And I'm putting these ellipses up to try to illustrate that we could actually have more than just these two simple input signals. To add more input signals, we would just add another resistor connected between our input signal and the non-inverting, or excuse me, and the inverting input terminal. Okay. So I'm going to have an input voltage here, V1, an input voltage here, V2. Here's my output voltage, and then I'm going to ground my non-inverting input terminal, right? So there's a couple of different ways that we could look at this particular circuit. I'm going to use the direct analysis technique that we've been using, and I'm going to use it for literally everything. But we could also look at this using superposition. And let's just talk about that very briefly, even though we're not really going to do it. So if the input voltage signal V2 were turned off or shorted out, what kind of amplifier would this look like? An inverting amplifier, okay? And then if the input signal V1 were turned off and V2 were left on, what would this look like? An inverting amplifier yet again. So we can realistically, we could analyze this by just figuring out what the output is for input signal V1, what the output signal is for input signal V2, and add those guys together. And we would get the exact same results as the analysis that I'm about to do. So we can always go back to different analysis styles if that makes sense. But for most of these, it's going to be simple enough to where we can just use a simple direct analysis. But good job understanding what the different constituent parts of this thing are. So no current flows in. By inspection, our non-inverting input voltage is 0 volts, which means our inverting input voltage is also 0 volts. And now we're going to have several currents to add. So we're going to add this guy and this guy and this guy together. So that's going to look like 0 minus V1 over R1. So negative V1 over R1 plus 0 minus V2 over R2. So that's going to be negative V2 over R2. I'm not going to add any more input signals, but we could see if there were other ones, they would just add another term there. And then we're going to have 0 minus V out, so negative V out divided by that resistor R. is equal to 0. And rearranging this, we find that V out is just going to be negative R times V1 over R1 plus V2 over R2. And I'm going to put some dots there for any subsequent terms that we might have. Okay. So we can't really define a closed loop voltage gain here in a general sense because we have multiple input signals. But we can pretty easily see that the voltage V1 is experiencing a voltage gain of negative R over R1. The input signal V2 is seeing a voltage gain of negative R over R2, etc. So each of these input signals is experiencing a different scaling factor, which is where the weighted term comes from. And because our output is dependent effectively on the sum of those weighted input voltages, that's why we have a weighted inverting summer. Okay. So this circuit effectively allows us to perform the mathematical operation of addition of different analog input signals, where each input signal is scaled by some different factor. If R1 is equal to R2 is equal to R3, etc. So all of the resistors on the input side are the same. And let's call that Rx for lack of a better term. Then our output voltage is simply negative R over Rx times V1 plus V2 and so forth. We no longer have a weighted inverting summer because all of the input signals are scaled or they're seeing the exact same voltage gain, right? So that's just an inverting summer because it's just scaling the output by a factor of R over Rx, and then all of the input signals are added together. So I'm not bored enough to do this, but realistically, I could actually compute you guys' grade in the course using a circuit like this. In as much as the input voltage V1 on a range from, let's say, 0 to 100 millivolts could be your score on exam 1. And I could scale it by the proper weight by setting up a resistor combination like that. The exact same thing for, so the input voltage V2 might be your score on exam 2, the input voltage V3 might be your homework grade, et cetera, et cetera. So you can do this for really anything. How many of you guys have ever crossed the state line, either going into Texas, Mississippi, or Arkansas, traveling by interstate? Probably everybody at some point, okay? Not, I feel sorry for you for having never left Louisiana. So every now and then you might find a weigh station that's actually open. The big load cells that are used to weigh trucks use a circuit like this, okay, where the input signals are being provided by electromechanical strain gauges. And then a circuit like this is used to add the output of each load cell together to give you the total weight of the vehicle. Very practical use. These are also used in your simple bathroom scales and all of that kind of good stuff. And it's the exact same thing. You just take the output of your different input, your input sensors, which are just strain gauges for measuring weight. They're output voltage changes depending on how much they deform, and then add those results together and it tells you, oh, this is how much you weigh. Scale, and that conversion between the output signal and the output of the sensors and converting it into a proper weight is handled just by those resistor values. So we have done the mathematical operation of addition. So now let's do the mathematical operation of subtraction. So this is what's going to be called a differencing amplifier. Differencing. So we might have something like this. So in my feedback loop, I'm going to have a resistor R. And between my inverting input terminal and my input signal V1, I'm going to have an additional resistor R. And these R's are representing the same resistance, so these are matched. On the non-inverting input side, I'm going to have my input voltage V2, and between that voltage and my non-inverting input terminal, I'm going to have a third resistor R, and I'm going to include a fourth resistor R here between my non-inverting input terminal and ground. So before we analyze this thing, I want somebody, let me do it this color. Tell me what that circuit is doing. You've seen it before in circuits 1, you've seen it before in this class. Jake, you keep looking generally at me. You got any thoughts? It's okay to be wrong. What's that? Yeah, this is a voltage divider circuit. 100%, absolutely right. So this one looks a little different than what we've done previously because we have a voltage divider circuit on the non-inverting input side, right? So we could analyze this one using superposition as well, effectively. So if V2 were on and V1 were off, this would look like a non-inverting amplifier with a simple voltage division stage added at the input, okay? If V2 were off and V1 were on, this would look like an inverting amplifier, where there's just a resistor connected between the non-inverting input terminal and ground. Put those guys together, and you're going to have an output that looks something like the difference of the outputs of an inverting amplifier and a non-inverting amplifier. And so now let's formally figure out how this stuff works. So ideal op amp rules, we have 0 amps here, 0 amps here. This is going to be slightly trickier than usual. What should the voltage present at the non-inverting input terminal be? Lee, since you were the one that correctly identified that this is splitting up that voltage, could you tell me what it's going to look like? Yeah, exactly half of the input voltage V2, because those resistors are identical. So exactly half of it's going to drop over this guy, the other half is going to drop over this guy. Absolutely correct. Okay. So applying ideal op amp rule number 2, we know that the voltage present at the inverting input terminal must also be V2 over 2. And now we can simply apply Kirchhoff's current law at our inverting input terminal. And so that's going to give us V2 over 2 minus V1 divided by resistor R plus V2 over 2 minus V out divided by R is equal to 0. And we could just multiply both sides through by R to get rid of those R's on the denominator. So as long as they're all equal to each other, doesn't really matter what size they are. All right, so now we have V2 over 2 plus V2 over 2, which to me just looks like V2. We have a factor of negative V1, and I move V out to the other side of the equal sign, and we get this relationship. Our output voltage is simply the difference between our input voltages. The reason why it works out this cleanly is because all of those resistors have the exact same value, okay? So we could introduce scaling and all of that kind of good stuff if we wanted to. So we could scale either the input signals individually, meaning that these two R's would be different and these two R's would be different and all of them would be different from each other. Or we could do something where, for instance, if we had this guy right here as 3R and this guy right here as 3R, what do you think would happen? It's gonna put a factor of 3 right there. So we can, I'm sorry. I just wanted to illustrate to you that you might see these sometimes and in some textbooks where the resistors aren't all exactly identical to each other. You might see it where each side has a scaling factor like that. And so I just wanted to illustrate kind of what that looks like and how it shakes out. Okay, so let's recap the different types of mathematical operations that we've covered to this point, okay? So the very first circuit that we looked at was the inverting amplifier, and that one gave us amplification and attenuation. The second amplifier that we looked at was the non-inverting amplifier, which just gave us amplification. Then we had our weighted inverting summer that allowed us to effectively add input signals together. Now we've looked at the differencing amplifier, which allows us to subtract input signals. We can't do addition and multiplication, or excuse me, we can't do multiplication and division with op amps particularly easily. So we're going to skip over those. And instead, we're now going to talk about how to do calculus with op amps. So an op amp can be used to perform integration and differentiation of input signals. And so both of these operations are actually based on the the inverting amplifier. But instead of using strictly resistors, we're going to introduce energy storage elements like capacitors or inductors. I'm going to derive everything using capacitors. And in one of your homework assignments, I'm expecting you to be able to derive one of these relationships using inductors. So realistically, I'm expecting you to effectively follow along with what I'm doing and just use the inductor relationships as opposed to the capacitor relationships like I'm doing. So just as a quick reminder, the current flowing through a capacitor as a function of time is equal to the capacitor value times the derivative of the capacitor voltage with respect to time, and we can rearrange this relationship to find that the voltage drop across the capacitor is equal to 1 over C times the integral from negative infinity to T of the current, stylus will write, flowing through the capacitor with respect to time. I'm using the representation here where we're integrating from negative infinity instead of some point in time where the capacitor voltage is known, just so that we don't have to necessarily think about the initial conditions on the capacitor. And then I will show you a way that we can always effectively force it to be zero once we do the analysis. So the first one that I want to look at is this circuit. And if I'm being honest, I can never remember which one is which, so we'll give it a name after we see how it works. I think I'm starting with the differentiator, but I might be wrong. So let's put a resistor in the feedback path like so. Let's put a capacitor here. This will be our input signal Vn, and I'm explicitly writing it as a time varying function because if it were a DC function, this wouldn't really do anything for us because we know that to see a current, we need our voltage to change, etc. So before we jump into the exact same analysis that we've done over and over and over again, I want to explicitly state that I'm going to treat my capacitor voltage, Vc of t, as having this polarity. So positive polarity on the left at the input side, negative polarity, or the input voltage side, the negative polarity is at the inverting input voltage terminal. And similarly, I'm going to say that my capacitor current, Ic of t, flows into the positive polarity terminal. Let me rewrite that a little cleaner. Okay. So we have 0 amps flowing into either one of our input terminals. We can see by inspection that the voltage present at the non-inverting input terminal is 0, and applying op-amp rule number 2 tells us that the voltage present at the non-inverting input terminal is 0. So now I'm going to write a Kirchhoff's current law expression. I'm going to do this ever so slightly differently, in as much as instead of saying current out plus current out is equal to 0, I'm going to say the current flowing in is equal to the current flowing out of that node, meaning that the current flowing into the node, which I've already defined as Ic of t, will be equal to the current flowing out of the node that I've just labeled in green. So that's going to look like Ic of t is equal to 0 minus V out, or negative V out as a function of time, divided by our resistance R. And I can do a trivial amount of rearranging here to find that V out as a function of time is then negative R times Ic of t, right? So using, this top relationship, that's going to look like negative R times C times the derivative of my capacitor voltage with respect to time. So now I need to figure out what the relationship is between my input voltage and my capacitor voltage. And that'll give me my relationship between my output voltage and my input voltage for the whole circuit. So anyone care to take a stab at what the relationship between VC of t and Vn of t is? They are the same, right? So Vn of t, we're treating as if it were a nodal voltage, meaning that the positive polarity terminal is at that left-hand node on the capacitor, and the negative polarity terminal would be at ground. Well, Vc has its positive polarity terminal at the same place, and its negative polarity terminal is at a node whose voltage is 0 volts. So while it's not actually ground, it is what's called a virtual ground. So we can say that Vn and Vc of t are literally the same quantities here. So that gives us the relationship negative Rc times the derivative of the input voltage with respect to time. This was indeed a differentiating amplifier. So let me write that name up here. So the last one that we're going to look at, I'm going to do this on this page over here, is then going to be the integrating amplifier. And it is going to be effectively the exact same thing, except that the capacitor and the resistor are going to trade places. So our capacitor is now going to be up here in the feedback position. Here's our resistor R, our input signal Vn, ground down here, output signal Vout. Let's define, I think I did it in purple, so I'll do that again. Our capacitor voltage Vc with the positive polarity on the left, which would be at the inverting input terminal, and the negative polarity on the right, which would be at the output terminal. And this will be my current IC of t. All right, so let's go through the steps of our analysis process. 0 amps are flowing into our input terminals. The voltage present at my non-inverting input terminal is 0 volts by inspection, which means the voltage present at my inverting input terminal is also 0 volts. And much like I did a moment ago, I am going to have Kirchhoff's current law equation, where I'm going to say that the current flowing in is equal to the current flowing out. So here we can see that our current flowing out, IC of t, is equal to Vn minus 0 divided by our resistor value, okay? We also know that the voltage drop across our capacitor is equal to 1 over C times the integral from negative infinity to t, the point in time that we're interested in, of current flowing through our capacitor dt. So substituting in our relationship for IC, this is going to give us 1 over RC times the integral from negative infinity to t of our input voltage. So we've got everything sorted out on the input side. So this time we need to figure out what the relationship between our capacitor voltage and our output voltage is. The output voltage and the capacitor voltage. It's not quite the same, right? So let me show you what I mean here. So I'm just explicitly drawing out V out of T here as a voltage present between that node and ground, okay? So the positive polarity terminal of V out is where the negative polarity terminal of VC is. The negative polarity terminal of V out is at ground, and the positive polarity terminal of VC is also at ground. So those voltages are equal in magnitude, but opposite in polarity, which means effectively that V out is just negative VC. So if I have VC over here on the left-hand side of this equal sign, I could replace it with V out as long as I remember to put a minus sign right here. And here is our integrator relationship. So, a couple of different things here. The first is we use that relationship for our integral where we went from negative infinity to positive to t, so that we wouldn't really have to worry about an initial condition on our capacitor. How that's handled in practice is usually by placing a resistor in parallel with that capacitor, where that resistor, if I'm remembering correctly, and I may not be, so I'm just telling you I'm doing this by memory, I believe that resistor needs to be rather large. Effectively, it's just giving the capacitor a way to fully discharge so that we can force the initial condition on that capacitor voltage to be 0. And then we can just go on from there, right? Okay, so let's talk about the differentiating amplifier and the integrating amplifier here really quickly, okay? So in this context that we're talking about today, we use these amplifiers to perform the mathematical operation of differentiation and integration respectively. However, they are also very regularly used in control systems for what's called PID control, so proportional integral differential control. So integrators provide the integral part of that. Differentiators provide the differentiation part of that. So they're part of control systems. They're also very regularly used in communication systems. We're going to talk about this later on in this class, but this differentiating amplifier right here is actually an example of a active, if I'm not mistaken, it's a high pass filter. And this integrating amplifier is actually can be used as an active low pass filter. I mean, where a filter is just a circuit that either passes or attenuates unwanted frequencies. Okay, and we'll talk about that much later in this class. So we've got all of these basic building blocks. So I would like to revisit the design projects really quickly with you guys. We can kind of talk our way through a couple of things here. So I believe I've already talked to you about design project number one, and effectively that's going to be a positive feedback Schmidt trigger circuit. And we already kind of talked our way through what that might entail. Okay. So let's look at project number two. In modern control systems, many sensors output a DC current whose magnitude scales in response to the size of the applied excitation. You are asked to design an op-amp-based converter circuit, which will convert a 4 to 20 milliamp input current into a 0 to 5 volt output voltage. Excuse me. The converter portion of the circuit should be a practical current source, which converts the input current into a voltage drop over an appropriately sized source resistance. And then the rest of the circuit is effectively going to be an op-amp that's doing whatever else is needed. Okay. So let's talk about this guy really quickly. This is probably one of my favorite design projects that I've given, and which you guys are usually kind of terrible at. So I'm going to give you some strong hints. Okay. So our ultimate goal here is to convert that 4 to 20 milliamp input signal into a 0 to 5 volt output signal. Okay. So we're going to use a practical current source in order to convert current into a voltage. So let me explain exactly what I mean by that. Let's do this down here. Let's call this design project number 1.2 hints. So let me start by asking you guys what I hope. I'm going to be mildly perturbed if it's not, but what I hope is a very easy question. What is a practical current source? Patrick, you're looking at me, take a blind guess. If you're wrong.
Like literally, or just like in a circuit? Like this is current.
In a circuit, how would we represent a practical current source? So this is an ideal current source, IS, right? A practical current source is just a current source in parallel with some resistance. You guys remember this at all? Am I just pissing in the wind here? So I'm going to define a set of terminals over here. And this is going to be the output terminals of our practical current source. Okay. So all right, so let's think about some things here. So on the input side, our change in current is from 20 milliamps to 4 milliamps, right? So what's that total change? The ultimate goal of our circuit is to provide an output voltage that ranges from 0 volts to 5 volts. So I would say that the change in voltage is just 5 volts. So I'm about to blow you guys' mind here by saying that our source resistance here should just be the change in voltage divided by the change in current. So somebody grab a calculator and tell me what that's going to look like. If it's not 312.5 volts, I've done it wrong. Or excuse me, 312.5 ohms, I've made a mistake, but I don't think I did. 312 and a half? Yeah. Go away notification thing. All right, so let's think about this really quickly though, okay? So if I have a 4 milliamp source in parallel with a 312.5 ohm resistor, what's my output voltage going to be? What? 1.25 volts, absolutely right. So that's on the low side of our swing. Now let's do the same thing, except we put 20 milliamps in. 6.25 volts, absolutely right. So the difference between those two is definitely 5 volts, right? 6.25 minus 1.25 is 5 volts. How am I going to get 0? That's where the op amp is going to come in, or the op amp circuitry is going to come in, okay? So the practical current source is effectively going to be connected to either the inverting input or the non-inverting input. It depends on how you choose to approach the problem. And then the op amp is going to be used to effectively get rid of that 1.25 volts of offset. How might we get rid of something or subtract something? A difference in amplifier, right? All right, so giving you extraordinarily strong hints about design project 1, problem 2. Let's look at problem 3. So the third one, a digital to analog converter is an electronic circuit which converts digital data, usually in the form of a binary number, into an analog current or voltage signal. I am asking you to design a 2-stage op amp. So this is technically going to bring into, it's going to require the use of something that we're going to talk about on Wednesday, which is cascaded op amps, but we can sort our way through a couple of things here. Design a 2-stage op amp network capable of converting a 4-bit binary number into its equivalent base 10 integer as a voltage output. And then I tell you a couple of constraints on how I want you to do things. So let's talk about this one a little bit here. Okay. So we have a 4-bit binary number, okay? So somebody tell me a 4-bit binary number. Doesn't matter what it is, just hit me with something. If you give me anything that isn't ones and zeros, I'm going to be furious. 1, 1, 1, 1. Okay, so 1, 1, 1, 1. I'm going to put a little line under each of these. So this guy right here is the 2 to the 0 bit. Then we have the 2 to the 1 bit. Then we have the 2 to the 2 bit. And then lastly over here, we have the 2 to the 3 bit, right? So to convert this into a base 10 number, we would have 1 times 2 to the 3 plus 1 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0, which should come out to be 15. Each of these bits is going to have its own voltage source that is either going to be a 0 or a 1. Okay? So let's talk very briefly about pulsed voltage sources in LT Spice, okay? There are some parameters that we need to pay attention to, okay? So the different parameters, and I'm going to try to do them from memory in the order that they are, but it might be different, is like the delay time, the value of the on voltage. I think we might have control of the value of the off voltage, but if not, it'll just be 0 for default. The rise time, fall time, period, maybe the number of cycles, all of those kind of things. Okay. I'm just moving this down a smidge. We're going to kind of make a little table here, as it were. So right here, let's do the 2 to the 0 bit, then the 2 to the 1 bit, then the 2 to the 2 bit, then the 2 to the 3 bit. Because what I want is effectively for us to cycle from 0, 0, 0, 0 all the way up to 1, 1, 1, 1. So it would go like 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and keep on going, so on and so forth, and all of that kind of good stuff. Okay. So which of these bits is changing the slowest? The 2 to the 3 bit is the one that's changing the slowest. Okay. So let's say that its period is one thousand milliseconds. Okay, just 1 second, right? So if the period of the 2 to the 3 bit is 1,000 milliseconds, and it's the one that's changing the slowest, what should the period of the 2 to the 2 bit be? I disagree. Let me write out these numbers. So we're going to start at 0, 0, 0, 0, then 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0. Gonna run out of space here, but I think you're gonna catch my drift in a moment. And so on and so forth, right? So effectively, to go through all 16 permutations, we have said that it's going to take 1,000 milliseconds. Okay. Now let's look at what's going on from here to here. Okay, this is half of a cycle. Okay, so whatever is representative in half of the cycle, the same thing is going to happen on the second half cycle or whatever. Okay, so this right here is the 2 to the 3 bit, then the 2 to the 2, 2 to the 1, 2 to the 0. So for this first half cycle, the 2 to the 3 bit is 0 the entire time, right? The 2 to the 2 bit is 0 half the time, and then 1 the other half of the time. So if the period of the 2 to the 3 bit is 1,000 milliseconds, what does the period of the 2 to the 2 bit need to be? 500, half as long. What does the period of the 2 to the 1 bit need to be? 250, there we go. And then 125 over here, right? So the periods need to be successively shorter by a factor of 1/2 in order for this to work out correctly. All right, so our rise and fall times, that's just the time it takes to transition from 0 to 1 and from 1 to 0. So let's make that just incredibly short. So like 1 nanosecond for everything. What do we want the voltage to be when our input signal is on or providing us our 1 volt? Like we want it, we're going to put ones and zeros in, and we're going to get 15 out, right? So V on is going to be 1 volt for all of them. V off is going to be 0 volts for all of them. If that's something that we control, I don't exactly remember. And then the delay is effectively telling us whether we want it to start at 1 or start at 0, right? So if we don't give it a delay, it's going to start on. If we give it a delay, it's going to start at 0, and then after the delay period has elapsed, it's going to turn to on. So the delay here should be 500 milliseconds because we want it to be 0 for half a cycle and then kick on. The delay here should be 250 milliseconds. The delay here should be 125. The delay here should be 62.5, and so on and so forth. And so we have these pulse voltage sources that are giving us effectively something that looks like this, right? So this is going to be, let's call it V3. V2. V1. And V0, where V3 is for the 2 to the 3 bit, V2 is for the 2 to the 2 bit, V1 is for the 2 to the 1 bit, V0 is for the 2 to the 0 bit. So this one should be off. And then it'll switch on and it'll effectively stay on. This one will be off and then on. And then off and then on, like so. Didn't give myself enough room to finish the full thing, but you should be getting the drift. Something effectively like this. Okay, so these are our input signals, which is, in my opinion, the hardest part of this thing. So using these input signals, how are we going to get an output that effectively just gives us 0 volts when everything is 0, and then 1 volts when this one is on, but the other 3 are off, and then 15 volts when all 4 of them are on at the same time? So a summing amplifier, okay. Does it need to be weighted or not? Yeah. Look what we did here, right? So Patrick gave me the binary number 1111. Each of these ones is an input signal. And each of these things, 2 to the 3, 2 to the 2, 2 to the 1, 2 to the 0, is a scaling factor, right? So we're going to use a weighted inverting summer. And then the second stage, and we'll talk about that more in class on Wednesday, is just going to be something that converts that negative number that we're going to get out, because our weighted inverting summer gives us a negative voltage signal. The second stage is just going to invert that inverted output to give us positive number. So the weights here are effectively 8, 4, 2, and 1. So we've got 4 different pulse voltage sources, each going into the input terminals of a weighted inverting summer, where the weights are 2 to the 3, 2 to the 2, 2 to the 1, and 2 to the 0. All right, so that's the third project. Nothing wildly difficult. Project number 4. Okay, so this is kind of tying things together. It is going to be a cascaded op-amp network. So again, we're not quite 100% there, but we have enough understanding going on. So for project number 4, we're asked to design a cascaded op-amp network, which can convert a 1 volt peak-to-peak sinusoidal input voltage into a 1 volt peak-to-peak square wave and a 1 volt peak-to-peak triangular wave. So let's start with the square wave because it's significantly easier. How are we going to convert a sinusoidal signal into a square wave? What's the output of a comparator look like? So for, let's say that we were dealing with a non-inverting comparator, okay? When the input signal is larger than the reference voltage, the output is VCC plus. When the input signal is less than the reference voltage, the output is VCC minus. So if I wanted a square wave from a sinusoidal input signal, I could use a comparator where VCC plus and VCC minus are the same magnitude, so that its output is going to be, positive, let's say 5 and negative 5. And then my reference voltage could just be 0, so that anytime my input signal is greater than 0, my output is VCC plus. Anytime my input signal is negative, my output is VCC minus. That's going to give me a square wave. So the comparator is what we can use to get our square wave output from our sinusoidal input. Now we need to figure out how to get a triangular wave as an output from either our sinusoidal input or our square wave. Getting a triangular wave out of a sinusoidal input is possible, but incredibly difficult. But it's way easier to get a triangular wave from a square wave. Let me put something back. I was going to say I'm going to draw it on the board, but I'm not going to do that. We'll do it here. Okay. So let's say that I have something like this. So it's high, and then it's low, and then it goes back to high, and then back to low, and so on and so forth forever. My goal is to get a triangle. So let's say that I'm starting, let me do it over here. So this is x of t. I'm going to call this a of t, where a of t is just the area under the curve x of t as a function of time. So when t is equal to 0, the area under my curve is 0. When I move out a little bit, the area under my curve is going to be positive. And when I keep on trucking, I'm going to have a curve like this. And now I've reached a point where I'm going to start adding in negative area. Didn't go quite far enough. So there's my negative area was taken away. Now my area is increasing again because this part is over it. And so I should have something like this, right? If I am keeping track of the area under the curve x of t. What's the area under the curve a fancy word for? An integral. So to go from a square wave to a triangular wave, we could just use an integrator. All right, so you have received, oh, we're 4 minutes past the end of class. Sorry about that. You have received extraordinarily strong hints on all 4 of the design problems. So you should be able to approach most of them now with at least some level of understanding of what you should be doing. It's up to you to figure out what components are necessary and all of that kind of good stuff. I am expecting you to just use the universal op-amp 2 for all of the op-amp circuits. So I really just want to know why you chose the resistors you chose, why you chose the capacitors you chose, if you choose to do one that requires a capacitor, etc. Okay. All right, see you guys on Wednesday for the end of our brutal look at op-amps.